Hi, welcome to this session on Axial Flow Compressor. Specifically, we are solving some numericals today. And in the previous session, we discussed about the work required by the compressor, work done factor, and degree of reaction, different ways of representing the degree of reactions, right? So in today's session, we will try to apply all the concepts into a numerical where you will understand a practical problem, how it can be solved using the known concepts. So let's get into it. So here is one numerical which talks about an axial flow compressor. A 10-stage axial flow compressor provides an overall pressure ratio of 5:1 with an overall isentropic efficiency of 87%. When the temperature of air at inlet is 15 degrees, the work is equally distributed between the stages. A 50% reaction blade design is used with a blade speed of 210 meter per second at a constant axial velocity of 170 meter per second. Estimate the blade angles. Assume the work done factor to be 1. So it's a very typical example of an axial flow compressor which is having a 10 stage and the overall pressure ratio is 5:1 and the isentropic efficiency is 87%, which is quite high. Then we have the inlet temperature, that is air is entering the compressor at standard sea level temperature, that is 15 degrees Celsius, and also the work is equally divided between the stages, right? And the degree of reaction of the blade stage is 50%, and the peripheral velocity of the blade is 210 meter per second. Now the constant axial velocity means CA. Here in the numerical itself it is given that the axial velocity remains constant, right? So that is 170 meter per second. Estimate the blade angles, right? So we need to calculate the blade angles, assuming the work done factor is 1. So we are assuming that there is no variation in velocity from hub to tip of the blade, right? So that is an assumption, but in reality there will be change and we need to consider it through work done factor. So here is the velocity triangle for the given problem and also the TS diagram. So velocity triangle for the rotor blade entry, let's call this as 1, and rotor blade exit, so let's call the section as 2. So we will start the analysis by calculating the rise in temperature in a stage, right? So the temperature change in one stage is equal to the overall temperature change in the entire axial flow compressor divided by the number of stages. Anyway, the value of n is given as 10. So then temperature change overall that can be represented in terms of the isentropic efficiency that is given in the problem. So the isentropic efficiency equation we are going to use, and from there we are going to calculate the overall temperature formula, and that is T1 by eta C. That is eta C represents the isentropic efficiency of a compressor, multiplied by R, that is the pressure ratio, to the power of gamma minus 1 by gamma, and this comes from the adiabatic relationship, that is adiabatic process, that is PV power gamma is equal to constant. So from this equation I can derive the relationship between pressure and temperature and density and pressure and density, right? So for a process, for an adiabatic process. So the first assumption here is the process is adiabatic, that is irreversible adiabatic. Why I am telling irreversible? Because it is a real process, the efficiency is given means the process is real. So isentropic efficiency is 87%. That tells that the process is a real process and we need to consider all the real flow analysis, right? So this is the basics about the relationship, adiabatic relationships. So then we have all the values, that is the inlet temperature we have, and number of stages, stage efficiency, the pressure ratio, and the gamma value is known, minus 1. So all the values we are going to substitute, and if I solve, I get the stage pressure temperature rise as 19.35 Kelvin, right? And now if I know the each stage temperature rise, so I can represent the stage temperature rise in terms of blade angles. So this equation we have derived in the previous class. Please go through it if you are not familiar with this equation. So again, before moving on, the question here is we need to estimate the blade angles, that is beta 1 and beta 2. So that is the reason I am following this method. First I calculated the stage temperature rise, and then I am using that stage temperature rise to calculate the blade angles, right? Very interesting method here. Now from this equation I can solve for tan beta 1 minus tan beta 2, and I know the value of stage temperature change, Cp, and work done factor that is given in the question as 1 u, that is the peripheral velocity, that is given as 210, and the axial velocity is given as 170, and that is assumed to be constant, right? So all the values are known, I just have to substitute, and I get equation number 1, that is tan beta 1 minus tan beta 2 is equal to 0.54, right? Now there are two unknowns, beta 1 and beta 2, both are unknowns and both are blade angles, right? So we will use the degree of reaction equation. So in the question it is given as the degree of reaction as 50%. See here, 50% reaction blade design. So I am going to substitute the value of degree of reaction as 0.5 and then derive the value for beta 1 and beta 2. So I get equation number 2 as tan beta 1 plus tan beta 2, that is equal to 1.235. Okay, this equation again we are getting it from the previous session for the degree of reaction, right? So please go through that equation if you are not familiar, right? So I have equation 1 and equation 2, and there are two unknowns, beta 1 and beta 2. So two equations, two unknowns, I can easily solve. So I get the value of beta 1 as 41.67 degrees and beta 2 as 19 degrees. So these are the blade angles at rotor inlet and rotor exit, right? So in the next session we will discuss another numerical, very interesting one, and I'll meet you in there.